If you have ever waited at a railroad crossing while a freight train rolled past, you may have noticed something ODD stenciled on the side of certain cars. 3 words in white block letters across dark steel. Do not hump. It sounds like a prank, but those 3 words are a safety instruction tied to one of the most physically violent operations in American freight transportation. How does a simple phrase on the side of a rail car connect to gravity, controlled collisions, and cargo worth millions of dollars? That's what this story is about. The story begins with a problem that railroads have been solving since the mid-1800s. A freight train pulling into a major yard might be hauling 80 or 90 cars, and every single one of those cars could be headed somewhere different. One boxcar might be destined for a warehouse in Houston. The tank car behind it might need to reach a chemical plant near Philadelphia. A covered hopper 3 cars back could be bound for a grain elevator in Kansas City. Those cars arrive together because they shared a stretch of mainline track, but they have no business staying together. They need to be separated, resorted, and reassembled into new trains headed toward their actual destinations. For decades, railroads handled this with a method called flat switching. A yard locomotive would shove cars back and forth across a web of parallel tracks, pushing and pulling individual cars or small groups into position. It worked, but it was painfully slow. A flat switching yard might need a full crew working an entire shift just to sort a few hundred cars. And as the American railroad network grew through the late 1800s and early 1900s, the volume of freight cars moving through major junctions swelled into the thousands per day. Flat switching couldn't keep up. So the railroads turned to the oldest force in physics: gravity. A hump yard is built around an artificial hill, typically between 15 and 35 feet tall, constructed between the receiving yard where incoming trains park and the classification bowl where outbound trains are assembled. The concept is deceptively simple. A yard locomotive pushes a string of cars up and over the crest of the hump. At the top, a yard worker uncouples the lead car, or a small group of cars, headed for the same destination. The uncoupled car rolls downhill under its own weight, picking up speed as gravity pulls it into the classification bowl below. But simplicity is not the same thing as gentleness. At the base of the hill, the track fans out through a series of switches called a ladder, branching into dozens of parallel classification tracks. Each track is designated for a different outbound train or destination block. As the rolling car passes through, the switches are lined to direct it onto the correct track, and at the end of that track, it slams into whatever car is already sitting there, coupling with a jolt that can be heard across the entire yard. One by one, car after car rolls over the crest, and train after train takes shape in the bowl below. The process is relentless and efficient, and at a busy yard, a new car can crest the hump every 15 seconds. The first recorded classification yard opened in 1876 at Mülheim-Speldorf in Germany. By the early 1900s, the concept had crossed the Atlantic and spread across the American railroad network. Early hump yards were crude by modern standards. Switch tenders lined the switches by hand. Brakemen rode the cars down the hill, working the hand brakes to control their speed. If a car rolled too fast, it slammed into the standing cars at the end of a classification track with enough force to damage both the car and its cargo. If it rolled too slow, it stalled partway down the track, and a yard locomotive had to go retrieve it in an operation called trimming. And here's the detail that everyone missed at the time. The real problem wasn't the switches, or the hills, or the braking. The real problem was speed at the moment of coupling. A loaded freight car weighing 100 tons, rolling freely at even 5 or 6 miles per hour, carries enormous momentum. When it strikes the standing car ahead of it, the impact ripples through both cars like a collision. Couplers slam together. Draft gear absorbs what it can. Everything inside both cars lurches forward. For a boxcar loaded with canned goods or machine parts, that jolt might mean a few dented cans or a shifted pallet. Inconvenient, but survivable. But what about a tank car loaded with chlorine gas? or 𝕼⁻⁻⁻? What about a flat car carrying 2 levels of brand new sedans fresh from the factory? What about a 100-foot passenger coach being repositioned across the country with no one aboard? This is where the 3 words come in. Do not hump is a mandatory stencil applied to any freight car whose contents, construction, or cargo cannot safely absorb the repeated impacts of hump yard classification. The phrase tells yard workers that the car must be set aside before the train goes over the hump. It needs to be flat switched instead, moved gently by a yard locomotive without the uncontrolled gravity roll and the collision at the bottom. The list of cars that carry this marking is longer than most people expect. Tank cars hauling hazardous chemicals are the most common. These include everything from crude oil and ethanol to poison inhalation hazards like chlorine and anhydrous ammonia. The coupling impact in a hump yard can stress tank shells, damage valves, crack fittings, and in a worst case, compromise the structural integrity of the car itself. Federal regulations impose strict speed limits on coupling moves involving hazardous materials cars, and some categories prohibit humping entirely. Loaded automobile carriers also bear the Do Not Hump stencil. A multi-level autorack might be carrying 10 or 12 new vehicles, each one secured on the rack by tire chocks and chain tie-downs. A hard coupling impact can shift vehicles against their restraints, dent body panels, crack windshields, and even cause cars to come loose from their mounts. For a manufacturer shipping finished inventory worth hundreds of thousands of dollars on a single rail car, even a minor impact is unacceptable. Intermodal flat cars carrying shipping containers or highway trailers fall under the same restriction. The containers sit on the flat car secured by twist locks, and a sharp impact can pop them loose or shift the cargo inside. Highway trailers riding on spine cars or well cars face the same risk. Their loads were packed for highway vibration, not for the abrupt collision of 2 rail cars, coupling at 6 miles per hour. Passenger cars being moved in freight service, sometimes called private varnish when they belong to charter operators or historical societies, also carry the Do Not Hump instruction. These rail cars have interiors designed for human comfort, not for industrial abuse. A single hard coupling impact can crack windows, break light fixtures, damage air conditioning equipment, and wreck anything that isn't bolted to the floor. Dimensional loads, meaning cars carrying cargo that exceeds standard clearance limits, also avoid the hump because their unusual size or weight distribution makes them unpredictable on the classification bowl's curved track work. There's another category that doesn't get talked about as often: cars carrying loads that are simply prone to shifting, like heavy machinery on flat cars or stacked lumber on bulkhead flats, also receive the Do Not Hump restriction when the shipper or the railroad determines that the securement can't handle a coupling impact. The Association of American Railroads publishes detailed switching charts that specify exactly which placarded and marked cars can be humped, which ones face speed restrictions during coupling, and which ones are banned from the hump entirely. It's one of the most granular safety frameworks in all of freight transportation. But here's the part that still doesn't make sense to a lot of people. If humping is so violent, why did the railroads build their entire classification system around it? The answer is that hump yards were engineered specifically to control that violence. In the early days, brakemen riding the cars down the hill were the only speed control. But by the 1930s and the 1940s, railroads had begun installing retarders, which are heavy steel mechanisms mounted alongside the rails that squeeze against a car's wheels to slow it down. The retarder works like a giant pair of pliers gripping the wheel flanges, converting kinetic energy into heat and noise. Anyone who has stood near a retarder in operation will tell you the sound is unmistakable, a high-pitched metallic shriek that carries across the entire yard. A typical modern hump yard uses retarders at multiple points along the car's descent. A master retarder sits near the crest of the hump and gives every car an initial speed reduction. Further down the ladder, group retarders at the entrance to each classification track cluster fine-tune the car's speed. Some yards also use inert retarders, Small passive devices embedded in the rail that provide drag through friction alone, slowing a car over the final stretch before it couples. In a modern automated hump yard, the entire process is controlled by a computer. Trackside sensors weigh each car and measure its rolling resistance as it crests the hump. The computer calculates the exact speed needed for the car to couple gently with the cars already standing on its assigned track, accounting for distance, grade, curvature, wind speed, and even temperature, because cold weather changes how freely a car's wheel bearings rotate. The retarders adjust automatically, gripping each car's wheels just enough to deliver it at the right velocity. Switches are thrown electronically, routing the car through the ladder without any human hands touching a lever. The target coupling speed in most yards sits somewhere between 4 and 10 miles per hour. That sounds gentle, but a loaded freight car can weigh well over 100 tons. Even at 4 miles per hour, the kinetic energy at the moment of impact is considerable. The draft gear, a heavy-duty shock absorber built into the coupler assembly, is designed to absorb that energy. But it can only absorb so much. And when conditions conspire against the system, when a retarder underperforms or a car rolls faster than expected, the results can be severe. There's a reason this system is still talked about today. It isn't a relic, and it isn't history. At Union Pacific's Bailey Yard in North Platte, Nebraska, this process plays out around the clock, every single day of the year. Bailey Yard is the largest railroad classification yard in the world. It covers 2,850 acres and stretches 8 miles across the Nebraska prairie. If you lined up all of its track end to end, it would reach 315 miles, roughly the distance from North Platte to Omaha. Every 24 hours, more than 14,000 railroad cars pass through the facility. Of those, 3,000 are sorted using the yard's 2 humps, one for eastbound traffic, standing 34 feet tall, and one for westbound, rising 20 feet. If you are enjoying this video and want to learn more about the engineering that keeps American railroads running, go ahead and subscribe. We cover stories like this every week. From an observation deck atop the Golden Spike Tower, visitors can watch the entire operation unfold below. 4 cars per minute roll over the crest, separate from the train, and drift silently into the classification bowl. 114 tracks fan out beneath you like the ribs of a giant steel fan. Each track is a thread in an outbound train being woven together, car by car, gravity doing most of the work. The eastbound hump at Bailey Yard crests at 34 feet. That doesn't sound like much, but for a loaded freight car weighing anywhere from 30 to 140 tons, it's more than enough elevation to generate the momentum needed to roll a quarter mile or more into the classification bowl. The westbound hump is shorter at 20 feet, reflecting the slightly different grades and track geometry of that side of the yard. But even at Bailey Yard, not every car goes over the hump. The do not hump cars are pulled from the train before it begins its climb. They are set aside on holding tracks and handled separately, flat switched into their outbound trains by yard locomotives. It adds time, it adds labor, and it disrupts the otherwise smooth gravity-fed flow of the operation. But the alternative is worse. The consequences of humping a car that should not be humped are well documented. The Transportation Safety Board of Canada investigated a series of overspeed coupling incidents at Canadian Pacific's Toronto Yard in the winter of 2003. In one case, a tank car carrying residue from sodium hydroxide was released from the hump and struck a stationary boxcar at roughly 12 miles per hour, well above the target coupling speed. In another, a tank car loaded with naphthalene benzene exited the group retarder at nearly 16 miles per hour. Both incidents caused damage to the cars, though fortunately neither resulted in a product release or injuries. The investigators found that retarder performance had degraded in the extreme cold, and that the yard's automation system had failed to account for the reduced braking effectiveness. So what happens when the system fails and a do-not-hump car goes over anyway? Testing conducted by the Transportation Technology Center in Pueblo, Colorado confirmed what railroaders already knew from experience. Higher impact speeds during coupling caused progressively worse damage, including cracked striker plates, broken brake hose castings, snapped uncoupling levers, and in one test, a cracked coupler. The researchers noted that the lateral position of the incoming car's coupler was a major factor in whether the coupling succeeded cleanly or resulted in a failure to couple event, where the cars bounce apart or override each other entirely. For a car marked "Do Not Hump," these are not abstract engineering problems. They are the exact scenarios the marking exists to prevent. The story of hump yards in North America is also a story about industrial decline. At their peak in 1975, 152 hump yards operated across the continent. Railroads invested billions in these facilities because they were the fastest way to sort the enormous volume of mixed freight that moved in individual carloads. A single hump yard could classify between 1,500 and 3,000 cars per day, a throughput that flat switching could not match. But the freight railroad industry changed. Mergers consolidated the Class I railroads from dozens of companies into just 6. Traffic patterns shifted. Intermodal freight, where containers and trailers ride on dedicated trains that run point to point without classification, grew explosively. Unit trains hauling a single commodity like coal or grain bypassed classification yards entirely. The carload traffic that hump yards were built to process entered a long, slow decline. Then came precision-scheduled railroading. PSR is an operating philosophy pioneered by railroad executive E. Hunter Harrison, first at Illinois Central in the 1990s and later at Canadian National, Canadian Pacific, and CSX. The core idea is to move freight cars faster by reducing the number of times each car gets handled. Pre-block traffic at its origin. Run trains on fixed schedules rather than waiting until a yard has enough cars to justify a departure. Swap entire blocks of cars between trains at intermediate points without breaking them apart at all. Under PSR, the hump yard, which exists specifically to disassemble trains and rebuild them from scratch, became something its proponents hadn't expected. It became the bottleneck. CSX under Harrison idled 8 of its 12 hump yards. Norfolk Southern shut down 4 classification yard humps in a single year at Allentown, Pennsylvania, Sheffield, Alabama, Linwood, North Carolina, and Bellevue, Ohio, as it implemented its own version of PSR called Top 21. Union Pacific decommissioned the hump at its historic Proviso Yard near Chicago, a facility that had been the largest hump yard in the world when it opened in 1929. A Union Pacific executive noted that Proviso was still using manual retarder operators to control car speeds into the bowl tracks, a method that hadn't changed in decades. Across the industry, the number of active hump yards dropped from 152 in 1975 to just 36. The decline wasn't driven solely by PSR. Railroad mergers had consolidated traffic flows and eliminated duplicate facilities. The long-term shift away from individual carload freight toward intermodal containers and unit trains meant fewer cars needed classification in the first place, and the cost of maintaining aging retarder systems at underutilized yards was becoming harder to justify. But the story did not end with closures. When freight volumes surged after the pandemic disrupted global supply chains, several railroads found themselves short on classification capacity. Norfolk Southern reactivated the hump at Brosnan Yard in Macon, Georgia. Shippers publicly credited the reopening of hump operations with helping to unclog the network and restore service reliability. A Koch Industries logistics executive told an industry conference that bringing hump yards back online had a measurable impact on freight movement across the system. Could the railroads have predicted that? Probably not, and the reversals came quickly. Union Pacific CEO Jim Vena put it plainly. "There is nothing wrong with a hump yard," he told investors. "It is the most efficient way to handle 1,800 to 2,000 cars a day. There is nothing better. It's low cost, and it works well." Meanwhile, BNSF Railway, which operates 8 hump yards on its 32,000-mile network, invested in replacing the master retarder at its Northtown Yard in Minneapolis, after nearly a decade of service and an average of 1,500 cars per day passing through it. The project involved tearing out the worn retarder, replacing the scale on top of the hump, and working across 53 bowl tracks to bring the facility back to full capability. So the phrase, "do not hump," is not just a quirky marking on the side of a rail car. It's a boundary line drawn between two worlds of railroad operation. On one side sits the elegant, gravity-fed efficiency of the hump yard, a system that has sorted freight by the force of physics for nearly 150 years. On the other side sit the cars that cannot survive that process, the ones carrying cargo too volatile, too fragile, or too valuable to be sent rolling downhill into a controlled collision with whatever is waiting at the end of the track. The next time you find yourself waiting at a railroad crossing, watching a long freight train crawl past, look for those 3 white words on the side of a tank car or an enclosed auto rack. They're a reminder that even in an industry built on brute force and enormous scale, some things still require a gentler touch. And if you want to see how railroads solved another one of their oldest engineering challenges, that video is on screen now.